Hi everyone, my name is Osmel Martinez Rosabal. I'm with the Center of Wireless Communications at the University of Oulu. The title of this presentation is Massive Wireless Energy Transfer with Multiple Power Beacons for Very Large Internet of Things. The agenda for this presentation. So first I will introduce the topic and then present the system model and how we formulate the problem. After that, I present a proposed solution and some key results. Finally, I will conclude the paper. So Internet of Things, it's a network that has gained popularity in the recent years. Some of the well-known applications are smart home, industrial Internet of Things, smart healthcare, gaming, surveillance, and many others. Internet of Things features a network of low power, low cost, and small form factor devices. Due to the popularity of this technology, some estimation targets massive deployment of 71 billion of Internet of Things devices by 2030. Due to the small form factor of these devices, they can only carry a tiny battery, which limits the lifetime of the application. To solve this problem, radio frequency wireless energy transfer allows replace devices' batteries over the air or even sustain batteryless devices operations. The energy receiver for this technology is known as rectenna, which is basically a rectifier. But why radio frequency WET is so popular for massive Internet of Things? So radio frequency, it's something that we can broadcast, and so we can power multiple users at the same time. Also, we can have a service provisioning under non-line of sight conditions. Radio frequency WET can also charge moving IoT devices, and due to the architecture of the energy receiver and the small size, it allows a seamless integration with the current transceivers. Some of the main limitations of the rectennas are the high sensitivity compared with the other state-of-the-art wireless information decoders. So around -10 dBm is already a high number. This, of course, limits the operational range of WETs to a few tens of meters because we cannot increase the transmit power deliberately. So there are two main directions for solving this problem. One is using energy beamforming, something that we have already used for traditional wireless communications. It's well known that for the case of optimum beamforming, we need the perfect CSI estimation. But for these cases with massive number of devices and a low complexity, also the energy constraints characteristic of this network, we can, in most of the cases, we cannot compute the optimum energy beamforming. But instead, we can rely on site information, which means the position of the devices or the antenna structure. And in other cases, we can use statistical channel state information which varies slowly with the time. Another way to overcome the sensitivity problem is by optimally deploying the energy transmitters or power beacons. This allows to eliminate blind spots in the networks and homogenize the energy availability. So here's our system model, which comprises a set of IoT devices powered by batteries. So how this works? The devices wireless link, which they use to update the battery state at some point, and then the power beacons compute the power allocation strategy such that they can charge the IoT devices to meet some quality of service constraint. The power beacons are equipped with an omnidirectional antenna and transmits independent energy carrier signal. The IoT devices have two main operational modes. One is sleep and the other inactive, which means that we have two different power consumption profiles. here's a problem. So we target the minimization of the sum power beacons transmit power to ensure certain energy at the device's battery at the end of the time, the charging time slot. So given certain ETH, which is a target energy at the devices, the minimum that we require the device's battery, we compute what is the optimal power allocation vector to meet this requirement at the end of the time slot. So, but what happens here is due to the path loss function, this problem is non-convex in the constraint 1b. And to overcome this issue, we propose splitting the problem into two problems. One is first solving the deployment optimization based on clustering. And then I'm fixing the transmit power. And then given that information, we optimize the transmit power of the power beacons. So because we have the device's position information, this is something that we know beforehand, we use the so-called k-means algorithm to divide the network in different clusters. But after that, we recompute the center of the cluster using the K-Chebyshev algorithm, which minimize the distance from each power beacons to its farthest device in the cluster. So, for example, take this picture on the right when you have 64 devices and 8 power beacons. So, as you can see, both strategies lead to different deployments, and the distance takes, for instance, this 7th cluster. You can see that K-Chebyshev can increase the contribution of the power beacon in the cluster because it is minimizing the largest distance in the cluster. So once we know the position of the power beacons, we can optimize the power. And this problem happens to be linear, which means convex, and we can attain the optimal solution. Let's evaluate, for instance, the cost using 0-point methods for solving this problem. So both iteration and operation depend on the number of sensor and the number of power beacons to obtain a solution with the accuracy. Besides, we can achieve an approximate strategy under certain conditions. So, for instance, if you have a sparse IoT deployment that leads to separate clusters, or the distance-dependent loss is sufficiently strong so that we can neglect the contribution of the neighbor clusters, we can achieve an analytical approximation of the power allocation strategy, the optimal power allocation strategy, in which the device with the highest growth of path loss and energy demands dictates the transmit power of the power beacon in its cluster. Of course, we have to bound the transmit power so that we cannot violate the maximum transmit power allowed for each power beacon. So some results, mainly we present here the outage probability and the sum transmit power, which is our objective function. So you can see these results are with respect to the energy demands of the IoT devices, the minimum energy that we are required for them at the end of the charging slot. As you can see, as we type these demands, the outage probability improves in all cases. The approximation achieves a better outage probability, but if you look at the picture on your right, you can see that approximation so it has poor results in terms of outage probability at the price of having lower transmit power. So of course it doesn't consider the contribution of the neighbor cluster, so it uses a lower transmit power. Of course, the performance is poor compared with the optimal k-means and K-Chebyshev. So of course, as the devices demand more energy, the power beacons are pushed to transmit with high power, which lowers the the outage probability, and of course increase the some transmit power. Here are some results with respect to the number of power beacons. So you can see that the approximation holds accurate for less than 6 power beacons in both cases, and always KHF outperforms the k-means algorithm, as we saw in the first picture. So something to comment in the picture on the right, you see that around 12, 13 power beacons, up to this point, the optimal transmit power strategy is to use the full allowed transmit power of the power beacons. And after this point, we have some gain. We can show some gain by using our strategy. So this shows how bad is the distance dependent loss for this network. So some practical consideration to take into account when implementing this proposal. So for quasi-static or mobile scenarios, clustering as a position strategy may require that the power beacons can also move or fly to update the position as the network changes. If the energy demands surpass the amount of devices, the amount of energy that devices can harvest during the charging slots, of course the system must schedule additional time slots for such devices, because of course they cannot achieve the required quality of services because of the limitations in the amount they can harvest during this time. And of course, because the battery feedback it's made in a wireless environment, wireless channel, it's subject to the channel impairments, and in some cases this information can be corrupted. So we propose here that the power beacons can validate this information in a distributed way using previous information, for instance, previous update, or maybe they can use the activation probabilities to estimate how much energy they need at a certain point, and then compare it with the updates. So that's it. So in this problem, in this paper, we address some power minimization problem of power beacons. First, by using devices position information, we use the KHF algorithm to position the power beacons, and given this information and using the device's battery states, we optimize the power allocation strategy. We derive in this paper an approximate strategy that holds when the contribution of the head power beacons dominates the incident radio frequency power within their corresponding cluster. So some implication of this solution is that because we are reducing the transmit power, we are reducing the power beacons energy consumption. There's something to take into account for green Internet of Things. And due to the optimal positioning problem of the power beacons, we are reducing the radio frequency wet link distance. This, of course, increases the incident energy with less transmit power. So this is all. If you have any question, please feel free to ask. Thank you.